So Philip Saidak's idea was inspired from Euclid's idea, as well as it was inspired from Goldbach's idea. Okay, let's see. So let n be a positive integer and consider this n1, first number n1 is n and n2 is n plus 1. Then obviously any two consecutive numbers, they are co-prime. So from these two numbers, so we'll have at least 2 prime because they are co-prime. Now so the number n1 times n2 must have at least 2 prime factors. Okay. Now you consider this number n3 is n1 times n2 plus 1. Now this n3, you can check that this n3 will be co-prime to n1 as well as this n3 will be co-prime to n2. Okay, so therefore from n1, n2, n3 you will get 3 primes, right? And you continue this process like you are then n4 will be what? n1 into n2 into n3 plus 1. So then n4 will be again co-prime to n1 as well as n2. It will be co-prime to n3 also. Okay, and this idea, you can see that it is like he is constructing a new numbers and which is pairwise co-prime. So basically he is constructing an infinite sequence and where the terms are pairwise co-prime. And this idea of adding 1, that is from Euclid's idea, right? So even if you see that in the case of Euclid's idea, P1, P2, Pn at the beginning, we consider like n prime number and n distinct prime numbers, they are of course pairwise co-prime. And then he constructed new number where capital N is basically P1 times P2 Pn plus 1. This capital N number actually co-prime to all Pi's. Okay, so that is the main idea. I hope all of you got the idea. Now, using from this Saidak's idea and Goldbach's idea, once I thought of creating a new sequence. Basically, if we are able to create a new sequence such that the terms are pairwise co-prime, then we are done. Okay, now let's see construction of a new sequence. So here I'll state a lemma. So given any n pairwise co-prime numbers, natural numbers, it is given n pairwise co-prime natural numbers, ni's. So we can construct a new natural number n such that n is co-prime to all of these ni's. Okay. So proof is very simple. So it is given that GCD of ni, nj is 1. Okay. And then what we let this set is, we call this, we collect all these ni's. Okay, we keep in one set. Okay, and then we divide this set into 2 disjoint subset. Okay, of course these numbers, this at the beginning, this small n must be bigger than equals to 2. Okay, so then only we can divide into 2 disjoint subset. At least 2 elements is required, right? So given any set, we can divide into 2 subset, 2 disjoint subset, such that their union is S. Yeah, that we can do. Now we are constructing a new number n, where this ni1 to the power alpha 1. So alpha i's are basically natural number. For the time being, you can thought this all the alpha i's are 1. For simplicity, you can thought this alpha i's are 1. So what we are doing, basically this first terms, this ni1, ni2, they are coming from this set A, and the next term, these ni's are coming from B set. Okay, it's very simple. First, you construct 2 disjoint subset. So first you take a product of all these ni's, where ni's are in one set, and the second terms is product of all those ni's, where the ni's are lying in the second set B. Okay, now what is our claim? claim is that this capital N will be co-prime to all of these ni's. Okay, so let di be the GCD of n comma ni. Okay, now di, since di is the GCD, so di will divide n as well as di will divide ni, right? So without loss of generality, ni must be either in A or in B. Okay, so first suppose now by our construction, either ni is in A or ni is in B. Now suppose ni is in A. Okay, ni is lying in A, then di will divide the first term, right? Because this is A, here is ni is present, right? Now di divides n as well as di divides ni. So that means di divides the first term. So therefore di will divide their difference. Okay, so therefore we can say that di must divide the second term, but di will divide the second term. That means that it must divide sum of ni's, right, in the from the B set. But the GCD of ni comma nj, that is given 1. At the beginning we have chosen all the numbers are pairwise co-prime, so di must be 1. Okay, so yeah, di will divide n. So this is what I have mentioned now. Since their GCD is 1, so di must be equals to 1. So hence we are done. Okay, it's very simple proof. So let me again say the lemma. So given any n pairwise co-prime numbers, okay, so we can always construct a new number n where that capital N is co-prime to the all the previous ni's. So basically at the beginning it was n pairwise co-prime number was given. Now you have n plus 1 pairwise co-prime number. And again, you continue this way. You continue this way to get infinitely many natural numbers, pairwise co-prime natural numbers. Okay, so that's I have mentioned it clearly here. So let n be any positive integer. Then let us consider this n1 as n to the power alpha and n2 is n plus 1 whole to the power beta. So now this idea of n1 and n2, you can see that it has the idea came from the Saidak's proof. Saidak first two numbers was n and n plus 1. So I just put alpha and beta any natural number. Then also it is okay. Okay, alpha beta, for simplicity, you can thought of alpha beta is equals to 1. Okay. Then Saidak considered the next number was n1 into n2 plus 1. Instead of that, you can construct n3 in this way, n1 to the power alpha 1 plus n2 to the power alpha 2. Then also your n3 will be co-prime to n1 as well as n2. Okay. So yeah. So here it means a GCD of n3 comma yeah, many times I may not write a GCD here. So but I mean GCD of n1 comma n2. Okay. Okay. Now once you have three numbers which are pairwise co-prime, now you have to construct n4. N4 will be like you can construct in many ways. Okay. Now you have to divide this a set of 3 elements into a 2 disjoint set. So you can make in 3 ways basically. Okay, you can construct n4 in this way, n1, n2 one side, and then you can also construct this way also, n1, n3 in one side. Okay, and then n2 and n3 in one side and n1s. Okay, so all this beta is for simplicity you can thought 1. Okay. So now this n4 also will be co-prime to all of these n1, n2, and n3, and you choose one of these forms and continue this process. Okay, infinitely many to get infinitely many pairwise co-prime numbers. Okay, and once you have an infinite sequence of pairwise co-prime numbers, then you will have infinitely many prime numbers, right? Okay. Now, let me once again show this Saidak sequence. You can see the table. Okay, like if we consider this is the Saidak sequence I have mentioned already. Okay, so corresponding to n equals to 1, you can see that n1 will be 1, then n2 will be 2 because n plus 1, and n3 will be 2 n1 into n2 plus 1, so that is 3, and n4 is 2 times 3 plus 1, which is 7, and so on. You continue this way. Okay. But this one is again corresponding to n equals to 2. You will get almost same sequence. Okay, because it's you are starting with 2, then 3 will come. Okay, 2 plus 1. Okay. And but for 3, n equals to 3 and n equals to 4, you will get a totally different sequence. And surprisingly, you see that so every time you are getting a new prime. So this 7 appeared here. Okay, but 7 won't appear anywhere because they are pairwise coprime. Okay, so in this sequence. Now let's see in our case the sequence is like, so n3 we have considered as n1 plus n2. So for simplicity, I have considered all these alpha is, beta is, gamma is are 1. Okay, n4 I have considered as n2 times n1 times n2 plus n3 and so on. So basically ni, I have only one term in one side. That is the pattern if you follow. Okay, then you will get, so every time you will get in these terms are pairwise coprime. So you can see that the sequence is totally different. Okay, so here if you see corresponding to n equals to 3, 3, 4, 7, 19, and 103. Okay, now let's go back and see. Here you see 3, 4, 13, 157, and so different. You are getting a different sequence. Okay. Okay. So now let me mention a few more open problems. Okay. So yeah. So basically, we are able to create a sequence of numbers where they are pairwise coprime, right? But what will happen, like whether the terms, individual terms are primes or not, whether we'll get infinitely many primes or not, that we do not know. So like in the case of Fermat numbers, it is not known whether there exist infinitely many primes in the sequence of Fermat numbers. Okay, so individual terms are primes, infinitely many primes will get or not. Okay, that we do not know. So similarly, same question you can ask, like whether there exist infinitely many primes in the Euclid sequence as well as Saidak sequence as well as in our sequence. Okay, like the divisors are giving you prime, but the individual terms. Okay, now if you see the table, so here you see 41 is prime. Okay, now this 130901, this is prime. Okay, but this 371 is not a product of prime. So we are asking that whether there exist infinitely many primes, like the terms of this sequence are prime. Okay, so that is it's difficult to answer. Okay, like Fermat numbers are, whether there exist infinitely many Fermat numbers are primes or not. Okay, so that kind of question you can ask for this sequence also. Okay. Now I'll mention a few more proofs, but these proofs are a little bit deep theorems, so it won't be easy to prove immediately. Okay, so Euler gave a proof which relies on fundamental theorem of arithmetic. So that is every integer has a unique prime factorization. So basically this right hand side series is known as a Riemann zeta function. So all of you may know about this series. It's one of the most important special function in mathematics. So this series is absolutely convergent and uniformly convergent on any compact subset of this domain. Okay, and this series can be written as a product of this infinite product. Okay, so where P is running over all primes. Okay, now if we assume that the set of prime is an infinite set, and if we let s tends to 1 from the positive direction of 1, then this series will become an infinite because it will converts to 1 by n. Okay, but in the left hand 1 by n series is diverges, right? So but in the left hand side, if we assume that there exist finitely many primes, okay, then it will be a finite quantity. Okay, so therefore you will get a contradiction. Okay, this is one simple proof. Again, Euler gave another proof where he proved that this prime counting function pi of x, it's counting prime up to x. X can be any real number. It can be any large real number. So that is, he showed that it will be bigger than log x minus 1 as x tends to infinity. And you know that log x is tends to infinity as x tends to infinity. So therefore, the number of primes will be infinite. Okay. So yeah, then prime number theorem. This is one of the most important theorem in number theory. So it states that this prime counting function behaves like asymptotically behaves like x by log x. So this theorem was conjectured by Gauss and Legendre, and later it was proved by independently proved by Hadamard and De La Posse. Okay, but so they mainly proved that the limit of x tends to infinity, and then pi x by x log x, that limit is 1. And you know that limit of x tends to infinity, x by log x, that goes to infinity, right? So pi x cannot be finite. So in that case, limit will be 0. So pi x, when x tends to infinity, must be infinite. Okay, it must grow like this function. Okay, x by log x, and limit x tends to infinity, x by log x is infinite. Okay, so this is not so easy to prove. So they proved like this result using the theory of Riemann zeta function, and people used to believe that without using complex analysis, this may not be able to prove. But later, Paul Erdos and et al. Selberg, they gave elementary proof of this independently. They gave elementary proof of this result. Okay, elementary in the sense that they didn't use any complex analysis, or they didn't use theory of Riemann zeta function. Okay. Sorry. Yeah. Now, next theorem is again one of the interesting result. Dirichlet proved that given any two pairwise coprime number a and b, the arithmetic progression a and a plus the starting with a and the difference is b. Okay, a plus b, a plus 2b, and so on. This arithmetic progression will also contain infinitely many primes. Okay, so but here you may wonder that why we need pairwise coprime number, because if they are not pairwise coprime, because then if their GCD is something bigger than 1, then each of the term is divisible by that GCD. So of course, then there is no point of asking that whether there exist infinitely many primes or not. Okay. Now you can see that the set of natural numbers, they are also arithmetic progression. So in the set of they are starting with 1 and difference 1. And more generally, one asks that any arithmetic progression has infinitely many primes or not, and that is true. Okay. So to prove this result, Dirichlet introduced one function which is known as a Dirichlet L function, which is a natural generalization of a Riemann zeta function. So using the theory of a Dirichlet L function, he proved that any arithmetic progression also contains infinitely many primes. Okay, now let me mention another result, Bertrand, which is known as Bertrand postulate. So now this is saying that for every n bigger than equals to 1, there is a prime p in between n and 2n. So now however large n you choose, you can always find a prime in between n and 2n. So once n goes to infinity, then you can say that we'll get infinitely many primes. But this result is saying much more than that. Okay. So this result was first proved by Chebyshev in 1850, and much simpler proof was given by Ramanujan. And even Paul Erdos, when he was just 19 years old, he also gave a proof of this result. Okay, but these are not so easy to prove. Okay, but one undergraduate student can learn this. Like in this this last 2 months, 2 undergraduate students from ISER Bhopal was doing one project under me, and they studied this thing, this Bertrand postulate. So interested student can see the proof of this beautiful fact. Okay, so yeah, there is a generalization of Bertrand postulate. So in 2006, Bertrand proved that there is a prime in between 2n and 3n for any n greater than 2. So you see, if we use Bertrand postulate, then in play you can say that in between 2n and 4n there is a prime, because the Bertrand postulate is saying that in between n and 2n there is a prime. Okay, so if you replace n by 2n, then from Bertrand postulate you can say that in between 2n and 4n there is a prime. So the gap is 2n. But this next result is saying a little bit more like more deep thing, like in between, not only in between 2n and 3n, for any n you will get a prime. Okay. But there is a folklore conjecture that for every k there is a prime in between k and k plus 1n. Like for example, k equals to, when k equals to 1 it becomes Bertrand postulate, when k equals to 2 then it becomes this result. But now you can ask that whether there exists a prime in between 3n and 4n for every n, but that is still not known. Okay, now I'm almost going to end, so I'll mention another famous unsolved problem, so which is known as Legendre's conjecture. It was proposed by Legendre. So there is a prime between n square and n plus 1 whole square. Okay, now you may ask that what is the difference between Legendre's conjecture and Bertrand postulate? So then if you substitute this n by n square, then Bertrand postulate is saying that in between n square and 2n square there is a prime. Okay, in between n square and 2 times n square there is a prime. So the gap is n square, right? But this result is saying that in between n square and n plus 1 square there is a prime. So the gap between these two numbers is 2n plus 1. Okay, so now the gap is like polynomial gap. So this is much more stronger than Bertrand postulate. Okay, but this is still open. Okay. So for a long time, people used to think that this conjecture was by Louis Legendre, but he was politician. Okay, but recently, few years back, mathematician discovered that actual Legendre was he was the mathematician who gave this. Many in the name of Legendre, there are many results in mathematics. Okay, so in 1980, Washington gave a proof using commutative algebra. Okay, and then in 1995, Furstenberg gave an interesting proof using topology. So it seems like they are totally different, but he connected. It's a really beautiful result. So interested student can have a look. So he introduced a topology on the set of integers. Okay, like their basis element he constructed as a sequence of arithmetic progression. Okay, so it's, and from there he got again using contradiction only. Finally, he assumed that finally many primes, then he will get a contradiction. And in 2009, Pinasco proved this theorem using this inclusion-exclusion principle. And Wang gave proved of this infinitude of primes using the the Polignac formula, so which is also known as Legendre's formula, which states that basically in n factorial, what will be the highest prime power dividing n factorial. Okay, so using that, so some of you may know that. Okay. So in 2010, Loknath Devnath gave a new proof using irrationality of pi. Okay, so mainly there is a Leibniz formula for pi. It's a product of an infinite product from where like in the denominator, it's like in the numerator, all odd primes are there, and in the denominator, prime by something which is the number nearest to the multiple of 4. Okay, so from there actually it's a very one-line proof. Okay, using irrationality. So if you assume that there exist finitely many primes, then one side, right hand side, will be rational number, and whereas we know that pi is irrational number. Okay. And there are several other mathematicians also proved this infinitude of primes in many different ways. So the story of infiniteness of primes started since 300 BC by Euclid, but still it's going on. So the main gist of this talk is that like this simple fact can be proved in many different ways. So I'm sure that some of you may try to prove this result in some different way, and I'm sure that some of you will get some new proof in future. With this, here is the some references. This is very nice book by Eichner and Ziegler. Proof from this book only I got inspired. So here in this book you will find 5-6 proofs of this fact. Okay, and this is also very nice book by Ribbenboim, Little Book of Bigger Primes. Okay, here is the reference of Philip Saidak and Furstenberg. And yeah, there are a few more references. Yes. So with this, I'm ending here. Yeah. Thank you for your attention.